Group activities are very common in current social networks. In a group, each member's different interests and preferences may have an impact on the final group decision. And therefore, group recommendation aims to reach consensus among group members and generate suggestions that can cater to most of the group members. In order to make a better modeling of the relationships between groups, items, and users, researchers have uncovered the hypergraph structure. In a hypergraph, a hyperedge can contain multiple nodes. Hence, it is naturally suitable for group recommendation scenarios where a group contains multiple members. And in addition, although excellent performance has been achieved based on various modeling methods, and the inherent specificity of group data is still diminishing in the model's performance, as groups are often formed temporarily. Thus, contrastive self-supervision is often combined as an argumentation signal to address the problem of insufficient data. Although most of the existing works achieve performance improvements by exploring hypergraph and contrastive learning, these methods rely heavily on accurate contrastive view generation. As shown in the figure, traditional methods often use randomly removed members to generate contrastive views, but the removed members may be key members that influence the group preference, resulting in the same entities as positive samples but with different preferences. This could yield incorrect results. In addition, group recommendation suffers from more aspects of noise than user recommendation, such as spurious interactions of users and groups, passively formed groups. Meanwhile, existing hypergraph neural networks for group recommendation over-entangle the information of members and items and ignore their respective unique factors in the message parsing process. To address above errors, in this paper, we proposed a novel disentangled hypergraph masked autoencoder for group recommendation. The input recommendation obtained from the embedding layer is first masked by a degree-sensitive hypergraph masking operation on high-degree entities, and then encoded by a disentangled hypergraph neural network, which learns the high-order relevant neighbor information to obtain the latent representation. At this point, it is divided into two parts. In one part, considering that members have different contributions in group decision, the group prediction score is obtained through dynamic preference aggregation to compute the group recommendation loss. In another part, the initial representation to compute the contrasted representation is obtained by second-time masked IMRP and is later used together with the initial representation to compute the autoencoding loss. In addition, due to the sparsity of group supervision data, the optimization objective of this model also includes user recommendation loss, which is trained jointly with the group recommendation task using user supervision data. For degree-sensitive hypergraph masking, we intend to mask high-degree entities that may contain a lot of redundant information and more noisy information with a higher probability. This strategy helps to reduce redundancy and enhance the hypergraph neural networks focused on low-degree entities. The formula on the right is how to calculate the probability of factor reservation. The factors of entities with higher degrees have a lower probability of being reserved. Using US as an example, the degree is the sum of the number of groups containing US and the number of items with which US interest interacts. For each layer of the Disentangled Hypergraph neural network, we capture the common and unique factors of members and items through a factor over disentangler. First, we capture the common factors of member information and item information in message parsing through the attention mechanism. Then unique factors are obtained by subtracting the common factors. The result of the transformation after concatenating the unique factors with the hyper-edge representation is added with the common factors to get the complete message, which is later passed to the nodes. Finally, we take the node aggregation message of each layer as the group representation of this layer, and sum it with the initial group representation to get the group representation after hypergraph encoding. Next, let me introduce our experiments. To prove the superiority of the proposed DHMAE, we conduct extensive experiments on 5 widely used data sets. Obviously, on group representation, our model outperforms all the baselines. Table 3 shows the results of the ablation study. We conduct 4 variants for ablation study without masked autoencoder, without hypergraph masked autoencoder, without degree-sensitive hypergraph masking by replacing it with a randomized strategy, and without a degree-sensitive hypergraph masking by replacing it with an opposite probability. The results of ablation study verify our MAE architecture significantly improves the ability of the model to provide recommendations, especially in terms of ranking quality. For the performance of hypergraph neural networks, we compare the common hypergraph neural networks used for group representation with our developed disentangled hypergraph neural network. And the results demonstrate the effectiveness of DHGNN and the necessity of introducing the disentanglement operation therein. Moreover, Figure 8 shows that our DHMAE has a significant resistance to spurious interaction noise interference compared to the suboptimal methods. The variant removing MAE and the variant with random masking strategy shows that the resistance of DHMAE to noise can be attributed to the masked autoencoder with degree-sensitive hypergraph masking strategy. At last, let me make a conclusion. We proposed a novel hypergraph masked autoencoder named DHMAE for group representation. We leverage generative and self-supervision technique to introduce self-supervised signals without data augmentation, and thus enhancing the model performance. To address the noise in group representation, we designed degree-sensitive hypergraph masking strategy to mask high-degree entities with higher probability. Meanwhile, we developed a disentangled hypergraph neural network that aims to capture unique factors of members and items during message parsing process. Extensive experiments demonstrate the superiority of our method. Thank you for your attention. Our code is open sourced, and you can find it at this link. Now, if you have any question, I'd be pleased to answer you.
Okay, thank you very much.